In this presentation, we will realize full subtractor using NAND gates only. We have already completed full subtractor. Now we will realize it using minimum number of NAND gates. This is the truth table in which A, B and B subscript I are the three inputs. D and B subscript O are the two outputs. Full subtractor is a combinational circuit. This means the output or outputs depends only on present input or inputs. The output or outputs depends only on present input or inputs. This is the definition of combinational circuits. Full subtractor is also a combinational circuit. This means these two outputs depends only on A, B and BI. A is the minuend, B is subtrahend, BI is the borrow input, or you can say input borrow. D is the difference, BO is the output borrow. And if you want to calculate D, the difference, then it is equal to A, minuend, minus B, the subtrahend, minus BI, the input borrow. And by using this, you can easily calculate the difference. Borrow output is equal to 1, or you can say high, whenever there is borrow involved. For example, in the second case, when A is equal to 0, B is equal to 0 and BI is equal to 1, we have difference equal to 0 minus 1. 0 minus 0 is equal to 0. So we have 0 minus 1. 1 is greater than 0. This means we need to take carry, and carry is equal to 2. We have already discussed this point while studying the number system. 2 minus 1 is equal to 1. So difference is equal to 1, and as there is borrow involved, borrow output is also equal to 1. So this is very simple thing to do. You can easily obtain the difference and borrow output for all these 8 cases. I have already written the differences and the borrows for all these 8 cases, and now we will obtain the Boolean expression, or you can say the minimized Boolean expression for difference and borrow output. And the best way to do this is to draw the 3 variable K map. 3 variable K map is having 8 cells, and when you draw the 3 variable K map for difference, and after solving the K map, the difference is equal to A XOR B XOR BI. And if you remember the full adder presentation, then sum S was also equal to A XOR B XOR CI, where CI is the carry input. So difference and sum we can implement in the same way, but the main thing is borrow output. And instead of directly writing the expression of the borrow output, I will first draw the 8 cell K map. And if you see A, B and BI, you can clearly see A is the MSB, the most significant bit, and BI is the LSB. And the information of MSB and LSB is very important while making the K map, because we have to write MSB first. So I will write A first, then B, and LSB comes at the end. 0 1 0 0 0 1 1 1 1 0. Now using the truth table, I will fill the K map 0 1 1 1. Let me change the color for this. 0 1 1 1. Then we have 0 0 0 1 0 0 0 1. Now we will make the pairs. This is the first pair. Let's call it 1. This is the second pair. Let's call it 2. And this is the third pair. Let's call it 3. So BO is equal to 1 or 2 or 3, and this is equal to 1 will give us A complement B, 1 will give us A complement B, or second group will give us A complement BI, A complement and BI, and the last group, the third group, will give us BI. So this is the expression of borrow output, and this expression is the minimized expression, but I will not use this expression because I want to obtain the full subtractor using minimum number of NAND gates, and to do that I will obtain a different expression for the borrow output. I will make different groups. I will first combine these two ones, and this will give me A complement and B. Then instead of combining these two ones, this one and this one like this, I will combine them individually, or you can say we will not combine them with other ones, we will take them individually. So that will give us A complement B complement BI. This one will give us A complement B complement BI, and this one will give us A and B and BI. Instead of using this expression for the borrow output, we will use this expression, and now we will realize the full subtractor using the NAND gates. Difference is A XOR B XOR BI, which is similar to sum. We will use 8 NAND gates to realize the difference, because we can implement XOR gate using 4 NAND gates. So I will first make 4 NAND gates. NAND gate is a universal gate, and we can implement any logical expression using NAND gates only. The other universal gate is NOR gate, and we can implement any logical expression using only the NOR gates like NAND gates, and because of this reason we call them universal gates. And right now we are implementing XOR gate using NAND gates, and for this we need 4 NAND gates, and you can see the connection. We have to connect the 4 NAND gates like this. Sometimes in your exam you will find this question. So this is how we can implement the XOR operation. D is equal to A XOR B. So this input is A, this input is B, and the output of this NAND gate is A XOR B. You can prove this by yourself. The next thing is A XOR B XOR BI. We can consider this output as one of the inputs to the 2-input XOR gate. A XOR B is, let's say, X, and BI is the other input, and the operation between them is XOR. So we again need 4 NAND gates. So I will copy this circuit. I will copy this circuit and then I will paste it. This is the next XOR gate. Okay, and the output of this XOR gate is the difference. This input here is BI, the input borrow, and the output here is A XOR B XOR BI, which is the difference. The next part is the implementation of borrow output, which is the most important part of this topic. But we will not implement borrow output in this presentation. We will implement it in the next lecture. So this is all for this lecture. In the next lecture, we will implement the borrow output of full subtractor using NAND gates only.